Good afternoon, my name is Iara Oliveira, and today I'm going to present to you the work called Effects of Normalizing Heat Treatment on the Mechanical and Magnetic Properties of an Ancient Iron Bridge. Here you can see the main contents of this presentation. I will start with a brief introduction about it, then I will show you the materials and the methodology that we used. I will also present to you the results, the main conclusions, and in the end some reference. First of all, I will talk more about the background of this structure. So this bridge was built between the years of 1864-1865, resulting in more than 150 years of operation. It has 173 meters, and it was initially built only as a railway bridge, but nowadays it is also used as a car crossing bridge, and the material used was the photo iron. All those informations are really important, especially when we talk about a maintenance service. Just like this bridge, we have many other structures all over the world made with the same type of material. So it's really important to understand how this material behaves and its main characteristics and properties so we can keep all those structures safe as you're still using many of them. It is known that ancient materials suffer a degradation process during time, and it has an impact on its microstructure and mechanical properties. So here, the main objective of this work is to characterize the effects of this degradation on the mechanical and magnetic properties of photoiron. On the first picture, on letter A, you can see the position of the profile study on the bridge. On letter B, you can see the profile itself, and it had some signs of surface wear and some plastically deformed regions, as you can see on picture C and D. First of all, we analyzed the chemical composition of this profile. Then, using the light optical microscope, we were able to analyze the microstructure of this sample that you can see on the images. And we were also able to quantify the amount of inclusions and analyze the grain size using the software ImageJ. Later, on the same sample that we used to analyze the microstructure, a hardness test was carried out. Again, on the surface S1, as we can see on the left image here, and it was used the Vickers scale. Then, using Sharpie bodies, we analyzed the impact resistance of those samples at room temperature. We analyzed samples with both longitudinal and transverse lamination direction, so we could evaluate how the direction of the inclusions inside this material would affect the impact resistance. For this analysis, we also had to deal with a geometric limitation of the profile. So the specimens here are smaller than average. So in order to be able to compare the results with the results we find in literature, in the end we converted our values using the international standards to an average specimen size. In accordance to evaluate the magnetic properties of this material, we first analyze it by the magnetic Barkhausen noise test. We analyze it on surface 1 and surface 2 of the same sample. The position of the sensor was in the center of the sample, varying 15 degrees, as you can see the marks on the images we have here. On the position of 90 degree, it is the lamination direction, and on the position of 0 degree, it is the transverse direction of lamination. The main reason to evaluate the magnetic properties of this material is to see if we can correlate these properties with the mechanical properties, and by using this non-destructive technique, if we would be able to identify the level of degradation of this material. On this table here, we can see the parameters that were used on both surfaces of the sample to make this analysis, and as an output, we had the root mean square of the Barkhausen noise signals. Using the same sensor of the previous analysis, we also obtained data about the hysteresis loop using a variable magnetic field, but with a maximum and minimum field fixed. On this table, you can see the input data, like the sampling frequency, excitation frequencies, and as an output, We obtain the magnetic permeability, the induction of remnant, the coercive field, maximum field, and maximum induction. In literature, it is proposed as a way to restore the initial state of the microstructure, this normalizing heat treatment, where the samples are under 950 degrees for about 2 hours and then cooled in air. Following these steps, we repeated all the tests with normalized samples. Looking at the chemical composition of this butyl iron, it is possible to observe a carbon content lower than most of the carbon values described in literature. On the other hand, we have a high amount of elements like sulfur, nitrogen, and phosphorus, which are elements that we don't desire to have high amounts nowadays, but it is a specific characteristic of this type of material. Looking at the chemical composition of all the structures and comparing the results between them, we can see, for example, that all of them have a high amount of phosphorus. But at the same time, if you compare the amount of phosphorus of each of them, you can see that has a high disparity between the results, showing that this material is not homogeneous. Analyzing the microstructure of this material, we are able to identify a ferritic matrix with coarse grain size and also rich in inclusions, small inclusions, but also big slug inclusions that are probably due to the manufacturing process of this type of Asian material. This result is in accordance with the results obtained by the chemical composition analysis. Comparing the images is observed no significant microstructure difference in both conditions. These results are different from the results presented in literature. So in this case, it is suggested a more detailed analysis using the scanning electron microscope. Using the software ImageJ, we are able to quantify the inclusions on both conditions, and it was noted a slightly decrease on the amount of inclusions for the normalized sample. On the other hand, after the heat treatment, the grain size suffered a significant increase, as we can see on the second table. In this test, we obtain high values of hardness, which is in accordance with the chemical composition analysis, since phosphorus and nitrogen can embrittle the material. After the heat treatment, we can see a decrease in the hardness values, probably due to the increase of the grain size. When we analyze other structures made with the butyl iron in literature, we can see that all of them also have high values of hardness. The standard deviation is also high, and this is probably due to the heterogeneous distribution of inclusions inside the sample. Since our material has high values of hardness, it was expected to obtain low values for the impact resistance. We can see here that both directions, longitudinal and transversal, has low values of impact resistance, but the transversal direction, the values are so low that it was impossible to convert to the values of our standard specimen. These low values observed are probably due to coarse inclusions, coarse grain size, and amount of small precipitates inside this material. After the heat treatment, the values are still very low, even lower than the post-operation condition. This is not in accordance with the results we find in literature, maybe because the increase of the grain size had a more impact on this property than the degradation of the material. Analyzing the magnetic Barkhausen noise, we are able to see that for both post-operation and normalized states, when we look at the direction of lamination, we can see a high anisotropy, but at the same time, a great amplitude of the MBN aligned with the rolling direction. Here, we could also see a tendency to equalize the MBN RMS values on the normalized conditions. For the 90-degree direction, there was a small decrease in values and an increase in the normal direction. This fact could be attributed to the residual stress redistribution inside the sample resulting from this heat treatment. Now, in these graphs, we analyze both conditions for the same rolling direction. The left graph is for the transversal direction, and on the right, we see the longitudinal rolling directions. We can see that the peak position in either of the graphs didn't change, but the ambient amplitude didn't suffer a great variation after the heat treatment. Now, analyzing the data by a polar graph, we can see that this material presents an easily magnetized direction on the longitudinal rolling direction, and that on both conditions, post-operation and normalized, they maintain the same curve behavior. This can be explained by the increase in the grain size, which decreases the anchor points and decreases the value of the MPa signal. This reduction in the MPa values may result from the possible solubilization of the precipitates inside this material and in the contours of the grains, which can also be anchoring points. Analyzing the hysteresis loop data for the condition of post-operation on both surface 1 and surface S2, we can see a high anisotropy for the 0-degree direction, the transversal direction, while the curves obtained for the longitudinal directions are very similar. Comparing the graphs, it can be seen that the maximum permeability and the maximum induction are the properties that most changed with the heat treatment, showing a general tendency to increase their values. This variation was more accentuated on the S2 surface, which also had the reminiscence value increased. There was no significant variation in the maximum field values for both surfaces, and a small variation of the corrosive field was noticed in the longitudinal direction, 90 degree, on the S1 surface, and on the normal direction on the S2 surface. However, this parameter did not show a consistent variation pattern. After all the analysis, we were able to observe an increase in the grain size as a result of the normalizing heat treatment, which led to a decrease in the hardness and toughness of the material here studied. An easily axis was also detected by the ambient technique, which maintained its orientation regardless the heat treatment applied, and there was also a strong correlation between the ambient results and the grain size increase of the material. This technique has a great potential, but it needs to be more studied to obtain a more concrete result. Here there are some references. That's the end of the presentation. Thank you for your time.